All right, so this is section 9.4, day 2 of our exponential growth and decay. Hope to get all this done in one video, but we'll see. Maybe it'll take two. The last problem is a little bit different, so we'll see if we have to do two videos here. Okay, so as we learned from day 1, um, we can take some kind of a differential equation, solve it, and then we get to what is called the typical exponential growth and decay formula, which it was we saw here. If we took some function like dy over dt, which was directly proportional to how y was changing, once you go through the process of solving the separable differential equation, we end up with the common formula y equals c e to the kt. What we should have seen is that c was the initial value of y and k was the constant of proportionality. We had exponential growth as long as the exponent of the exponential, was positive. So as long as k was greater than 0. And then we had exponential decay as long as k was less than 0. And if k is 0, then the e part becomes 1, and you really don't have an exponential function anyway. It's just constant. So we don't typically list that one. All right, these are just, for the most part, going to be some more examples. If you've gotten pretty much everything from the prior lesson, you probably don't need to worry about all of these examples. It's just extra help, except for the fifth one. The last one is going to be the most important. Okay, a village had a population of 1,000 in 1980 and 1,200 in 1990. Assuming the population is experiencing natural growth, what will be the population in 2010? So we're trying to extrapolate a little bit here based upon the information. All right, so we don't have to go through the entire process of saying, okay, now we have a differential equation, let's go ahead and solve it. It's telling us it's experiencing natural growth, which we know is P equals C e to the kt. So if you see that, you don't have to go through the entire process. All right, let's see what we know. We need to find C and K in order to solve anything. So C is the initial population. It says that's 1,000 in our initial time of 1980. And then to find K, we're going to need a second population as well as the time that goes with it. It tells us the new population is 1,200. In 1990, which is from 1980, 10 years, so T is 10. And then we still have K up there. That's K. So let's solve this thing for K. Let's divide both sides by 1,000, which should give us 12 over 10, which is 6 over 5. We can then take the natural log on both sides to get the 10K out of the exponent. So we get the natural log of 6/5 equals 10K. Solving for K, we'll divide by 10, which is the same as multiplying by 1/10. So there's our K value. Plug K back in. We have our population equation as 1,000 e to the 1/10 natural log of 6/5 times t. And it wants to know what the population is going to be based upon this model in 2010. 2010 is 30 years from 1980. So we'll plug in a 30 for t. This one can actually be done by hand. We are not going to, but it can. Because plugging 30 in there for t actually gives us a very nice whole number. P of 30 ends up being 1,728 people, I guess, for our population, although it doesn't say people, it just says the population. All right, number 2. Radioactive decay is measured in terms of half-life. So here's kind of our biological sciences. Not really the word I was looking for there. Deal a lot with half-life and chemistry and things like that. Suppose that 10 grams of plutonium isotope 239 was released by the Chernobyl nuclear accident How long will it take for the 10 grams to decay to 1 gram? It tells us that the half-life of plutonium is 24,360 years. That is a long time for this isotope to decay. So let Y equal the mass in grams of the plutonium. Because the rate of decay is proportional to Y, we know that we can use the standard growth model. So let's see, what do we know? We know that the initial amount that they gave us was 10. Oops, not C. C is 10. And it tells us that the new amount is 1. That'll go in for Y. And it tells us it takes 24,360 years for this thing to hit its half-life. So we can't actually use 1 because 1 is not the half-life. In order for it to be a half-life, it has to decay to half of what we started with, which should be 5. And then we're going to have 24,360 times K. Okay, so divide both sides by 10. Guess what we get on the left? 1/2. That is not a coincidence because it is half-life. We'll take the natural log of both sides, and we get the natural log of 1/2 equals 24,360 K. So K is going to be dividing by 24,360, 1 over 24,360, natural log of 1/2. So we can plug that back in, and we get Y equals 10 e to the 1 over 24,360 natural log of 1/2 times T. It wants us to figure out when this is going to decay to 1 gram. So we're solving for T. So now the Y value becomes 1. And the worst part about this whole problem is rewriting that 1 over 24,360 so many times. So to solve for T, we'll divide by 10. We'll take the natural log on both sides. We did this plenty of times in our other videos. So you should be able to now figure out what T is. And T is going to be approximately, according to this, 80,922.168 years. That is a long, long time. All right, make sure that if you're going through this process along with these examples, that you can get that number when you use your calculator. Example 3. 1 hour after a bacteria culture was started, there were 300 organisms, and 2 hours from the start, there were 900. How many organisms will there be 4 hours after the start? Again, we can expect exponential growth here. So we'll start off with Y equals CE to the KT. We know that the C value, let's see, 1 hour after we actually don't know the C value. What it tells us is that 1 hour after the culture was started, there was 300. So we can use that as our C value. That's our only starting position. And then it tells us that 2 hours after the start, so there's our new value, we have 900. We have to be careful here, though, because the first one was 1 hour after. The second one was actually 2 hours after. So the time difference between those two is actually just 1 hour. So in this case, T is 1. So then we just get 1K up there. So let's divide by 300, which will give us 3 equals e to the K. Take the natural log of both sides. We get here that K equals the natural log of 3. So our exponential growth formula is Y equals 300 e to the natural log of 3 times T. It says how many organisms will there be 4 hours after the start? Remember that our initial value was 1 hour after the start. So 4 hours after the start is actually only going to be a T value of 3. So we're going to plug in 3 for t, so this will be a y of 3 equals 300 e to the ln of 3 times 3. Again, this one works out to be actually really nice. Y of 3, plugging all that stuff in gives you 8,100. 8,100 organisms 4 hours after the start of that particular problem. Okay, number 4. A sample of an isotope initially weighs 90 milligrams. After 100 days, 60 milligrams remain. After how many days will the sample be down to 20 milligrams in mass? Okay, again, same idea. Y equals C e to the kt. This thing is decreasing, so it should be a negative k value here. Let's see, the initial value is, for C is 90. The second value here is 60, and that occurs 100 days after the original, so that's going to be 100 times k. Solving for k, we're going to divide by 90. 60 over 90 is 2/3. Take the natural log of both sides, and we get the natural log of 2/3 equals 100k. So then k is going to be 1/100th of the natural log of 2/3. Natural log of 2/3 is a number that is negative because the argument is between 0 and 1, so we're good. This is decay. So we get that y equals 90 e to the 1/100th natural log of 2/3 times t. It says after how many days, so it's asking us about time. We need to solve for the time. Will we be down to 20 milligrams? So we'll plug a 20 in for y. And once again, we're going to go through the steps without writing them down. You would divide by 90. After you do that, you'll take the natural log of both sides, getting rid of the e, and then you'll divide by the 1/100th natural log of 2/3 to get your t value, which in this case works out to be about 370.951 days. That's how long it should take to get down to 20 milligrams. All right, our last problem. This one's a little bit different. This is what is called Newton's law of cooling. And Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings. So I'm going to be honest with you, this is really exactly the same problem. The only thing that's different is that instead of just having a single variable attached to your k, it is the difference in the surroundings. I actually like to add a little O down there. That should be an O. It's not erasing. There we go. Just for the temperature of the object itself. Otherwise, this is exactly the same idea. We've got dt over dt, which I mentioned in the previous videos. That's kind of weird. Call that the temperature of the object right there. Otherwise, this is exactly the same thing. It's just you have to be careful on it. That's all. So let's go back down to here, and we're going to see that this works out to be exactly the same as what it did before. So it says a bottle of soda pop at room temperature 72 degrees is placed in a refrigerator where the temperature is 44 degrees. Okay, not unreasonable. After half an hour, the soda has cooled to 61 degrees. Again, not unreasonable. Started at 72, put it in something which is 44, it's starting to cool, it's now down to 61. So part A says, what is the temperature after another 30 minutes? And technically this should be a part B, just wasn't labeled. How long does it take for the soda to cool to 50 degrees Fahrenheit? So let's deal with part A first. Okay, so remember that this is the equation we're starting off with. Again, I'm going to put that little O there for the surroundings. So this is what we have to remember. We're just going to kind of replace that t sub 0 minus t sub s, not t sub 0, t sub o minus t sub s. We're just going to call it y, because that's really what it is. It's just our y, but our y is the change of temperature. this case. All right. Our C value, when we get to it, will also be a change of temperature, but we'll see that. So we know that if we just replace T sub O minus T sub S with Y, this is what we get. That's your exponential growth and decay model. So what that's going to say is that Y equals C e to the KT. Okay, not a big difference there. So Y we already know is the change of the temperature. C, because it's an initial temperature, is also technically a change of temperature. It's always going to be the temperature of the object minus the temperature of the surroundings. So we'll write that down. C is also a change of temperature minus the change of surroundings. It's just a different one. So let's figure this out. The C value is the initial temperature. Well, the initial bottle temperature was 72 degrees, but we placed it into a surroundings of 44. So really what the C value is the change or the difference between those. So 72 minus 44 in this case. So C is 72 minus 44. 72 minus 44 is 28. So that's our C value. It says after half an hour, the soda has cooled to 61. Well, that's our Y value, which is also a change in this change in the temperature. So that would be 72 minus the new temperature of 61. Oop, I apologize. That is not right at all. It's the new temperature. Geez, come on, erase. Okay, the first one was right. I don't even know why I erased that. 72 minus 44. It's actually 61 minus 44. That's the new temperature. 61 minus 44 is 17, so that goes on the left. And then we don't know K yet, but the T should be 30 minutes. So 30 K. And then we can solve for K. 17 over 28 equals e to the 30K. Take the natural log of both sides. The natural log of 17 over 28 is 30K. So K is 1/30th of the natural log of 17 over 28. All right, we're almost there to be able to at least get the first part done here. So let's see, we've got Y equals C, which is 28, e to the 1 over 30, natural log of 17 over 28 should be decay, times T. And it is asking us in part A, what is the temperature after another 30 minutes, which means that it's actually going to be after 60 total minutes, because that would be an hour after we plug this thing in. So we're going to do Y of 60, which is 28 e to the 1/30th natural log 17 over 28 times 60. Plug all that stuff in your calculator, and we get, what do we get here? We get that Y is going to be approximately 10.321. I plug that in correctly to the calculator. All right, so something should strike you as odd here, because we plug this thing into a 44-degree refrigerator, and now it's telling us that the temperature is 10.321 degrees. That cannot possibly be right. Can't actually go below the actual temperature of the refrigerator. So you have to think, well, Y was actually what? Y was actually right here, change in the object minus the change in, change in the temperature, which was the temperature of the object minus the surroundings. So Y itself is T sub 0 minus T sub S, we are trying to actually find the temperature of the object, so we have to add that temperature of the surroundings back in. So the actual temperature of our object at 60 minutes is 10.321 plus the original difference of the surroundings, which was 44 degrees. So the actual temperature of our object at 60 minutes was 54.321. That makes a lot more sense. Cooled down to 54 degrees. All right, so all of this down here in blue was part A. Part B, be a little bit quicker and easier because we've done most of the hard work. Part B says, how long does it take for the soda to cool to 50? Well, we've actually already gotten to the point where we can use the equation we got in part A. So we'll put a 50 in for Y. Actually, that's not true because 50 is not the object minus the surroundings. The object minus the surroundings would be 50 minus 44, so that's 6. And that's going to equal 28, e to the 1/30th natural log 17 over 28 times t. And then once again, this is just calculator work. You'll divide by 28, take the natural log on both sides, divide by 1/30th natural log of 17 over 28, and we get t is approximately 92.613 minutes. So it's going to take a little over an hour and a half to get to that point. All right. If for some reason then some of that didn't make sense, again, watch this particular problem again. Hopefully it does, because it's really just the same process. The only thing you have to remember is that the C and the Y values are the differences or the change of the temperatures. That's the biggest thing. And it's always going to be the object minus the surroundings. All right, not too bad, a little over 22 minutes for this video. That should finish it up. We have one more section to go in chapter 9, which is going to be 9.5. And again, it is part of the book in the newer books, but it's still separated in the older book.